please send it as a direct message to Implexis Q&A. For those of you who are attending in person at the Congress Center, you can send your questions to him through our staff. Today, we are joined by Daniel Oblak. Daniel Oblak is a Canadian physicist, expert in quantum communications and quantum cryptography. He is currently a professor at the Institute of Quantum Science and Technology at the University of Calgary and received his Master in Science in Physics and Mathematics from the University of Aarhus and his PhD from the Niels Bohr Institute of the University of Copenhagen, where he demonstrated spin comprehension in the atomic clock transition. In Calgary, he started working on implementation of quantum memories using cryogenically cooled rare earth ion doped materials and participated in several important demonstrations, such as the first entanglement storage in a solid state material and the development of a quantum repeater architecture based on spectral multiplexing. Eventually, his research work was extended to other aspects of quantum communication and networking, such as photon source and detection components and RF optical transducers. Subsequently, Professor Oblak served on the board of the Postdoctoral Association for several years and acted as a representative on the University of Calgary's Governing Council, as well as other committees. Daniel Oblak has continued research activities at Calgary as director of newly created Quantum Cloud Lab. Welcome, Dr. Oblak.
Thank you for the introduction. Oh, wow, I'm so loud here. Okay, so I have to share my screen, right? Okay, let me just do that. Give me a second here. It's much more fun if you can all see my talk, actually. Share. Ooh, looks about right. Make sure that that's the right. Oh gosh, yeah, I didn't change the date here. I copied it. So it's actually May 21st here. Anyway, that's probably not too bad. Okay, and now we're gonna go presentation mode. All right. Okay. All right. Well, yes, again, let me just test this. Yeah. Okay, good. Thank you. So thank you so much for the organizers for inviting me here. When I got the invitation, at first I was thinking like, what is this? I've never heard of this, which is my mistake. But then I looked it up and I thought, wow, you guys had Nobel Prize winners on a regular basis here. And so like, that's a good company. I should go there. And then after having not traveled for about 2 years because of COVID, I thought like, this is my chance to get out of the country. And so it turns out that it's a really, really great conference here or symposium with lots of interesting speakers. I've learned a lot from some of the other speakers that are really outside of my field and some that are inside my field. So it's actually been a really, really nice thing. And I even, for my first time ever, I managed to get through a whole lecture or a presentation in Spanish and actually understand what it was. That was the one on the black holes. I was sort of at a level where I could sort of follow. It's really amazing. So lots of good things, and I hope I can give a little bit back now by talking about our research and sort of the concept of quantum networks. And before I get to that, I just want to introduce a little bit about what quantum sort of research is going on at the place where I'm in. So there we go. So as I was mentioned, I'm at the University of Calgary, which is in Canada, and you guys have plus 40 degrees centigrade. We tend to have minus 40 degrees centigrade. So not all the time, as you can see, it does get summery and warm. The University of Calgary is, a fairly large university, and we have about 33,000 students. Here's a picture of it with the university in the foreground and the downtown Calgary in the background. And the quantum aspect of the research at the University of Calgary is centered on the Institute for Quantum Science and Technology, which I guess is, getting close to 20 years now since it was inaugurated. And it has faculty members from not just physics, but also computer science, chemistry, and mathematics, because there are aspects of quantum that are relevant to all of those fields. And so it's sort of an interdisciplinary center. We've grouped it into these 4 main areas of research. There's another initiative going on right now, which is called Quantum City, which is aimed at bridging the gap between university research and industry. So we have industry partners. There's a big industry partner that joined the effort already, and there'll be more. And so the aim is to grow with a whole bunch of different programs, new faculty hires over the next couple of years, new programs, and several innovation zones. And one of the sort of very interesting things from a point of view of a researcher is that we're going to have a nanofabrication lab built also over the next 5 years or so. So really exciting stuff where quantum is being pushed forward and forward on the provincial level and also on the federal level in Canada. So there's a little lag here. Whoops. No, it doesn't work. I think it's because there. Okay. Sorry. I think it's just, let's see. No, it's because if it goes out of, like, I think if it goes out of the PowerPoint but onto the Zoom, then it doesn't react. Okay. So where do we fit? Well, so I am the head of the Quantum Cloud Lab, and for those of you who have any knowledge of Slavic languages and know what my surname means, you can tell that I've actually named the lab after myself. But quantum cloud refers to quantum networks more generally as building a network that works on quantum principles. Calgary and the area is beautiful. So if you like nature, it's also a good place to go. This is all the pictures on the website I took myself, and this is a very pretty place where we have a glacier dropping into a mountain lake. And if you want to read a little bit more about the lab and sort of connect on social media, there's a couple of links there to all our presence online. Okay. So, and here is who we are as of last summer, I think. And we're a couple of more people, but right now we're about 20 people, sort of postdocs, research associates, graduate students, and undergraduate students. And you'll see that we have quite a lot of projects going on in quite different areas, and we'll cover some of them, or I'll cover some of them today, but not sort of all of what we're doing. So if you want to hear a little bit more, then I can talk a little, I can talk in person with you also. Okay, so what are we going to talk about today? I'm going to talk about quantum networks. And briefly, I'm going to talk about the different applications of quantum networks. So what can you use them for? Why build them in the first place? That's going to be more me explaining a couple of things. And then I'm going to go into some of the considerations for what you should think about when you build quantum networks. Specifically, there's a question of how do you transfer the quantum information from one place to the other. And one of the very determining factors for that is really the distance over which you want to communicate. And so I'm going to try and present systematically how one considers that. And then at the end, we're going to talk some of the key components that you would want sort of on the hardware side for building quantum networks. Admittedly, I'm going to focus more or less only on the quantum memory because that's the one that is actually the hardest and the one where we have a lot of research going on. But I will touch upon the other devices as well that are needed. Okay, I have a nice background beat. So I should do a rap here. Okay, again, okay, let's see. Every time there's a message popping up, then the clicker goes away. Okay, all right. So what is quantum? What are quantum networks good for, and what are some of the applications? So there are three main sort of areas or pillars where you can say quantum networks can come into play. One of them, for all of you who were at the tutorial yesterday, will know about quantum key distribution. So the point of quantum key distribution is that we communicate a lot right now in our information society over long distances with each other. And some of that information we want to keep secure. We don't want people to look at our banking information, our private messages and whatnot. So we want to keep it secure. And of course, we have encryption that does that. But it turns out that when you look at the current encryption protocols used over the internet today, they're based on some assumptions on the computational difficulty of certain mathematical problems. It's more specifically the prime factorization problem, which turns out to be hard. But that has a problem. First of all, computers get better and better. So what's hard today is maybe not hard in 20 years from now. And if you want to keep your message secret for longer than that, well, then that's a problem, because it's not going to be secret for that long. If somebody stores it, they can decrypt it in, let's say, 15 years from now, and maybe reveal some national secret or whatnot that you really would like to keep secret for a little bit longer. Secondly, mathematicians are at work. As I said yesterday, I'm not quite sure how and what they do, but they do solve things. And they do make new algorithms. I'm just saying that because I'm not a good mathematician necessarily. You know, these hard problems are hard just because there is no efficient algorithm for solving the prime factorization problem. But with advances, you could think that suddenly somebody comes up with a new idea and it's done for, and the problem is become an easy problem. And so there's a potential that that could sort of undermine the full cryptography system that we currently have. And finally, which is, you know, the interesting thing about quantum technology, that the quantum computers, once they get developed to be large enough, actually have a known method for breaking this prime factorization problem. This is what Tony Leggett was talking about as one of the protocols that was discovered for, you know, how to use quantum systems for quantum computing. So lots of problems potentially, and you know, we can sit around, wait for, you know, things to happen, and then not try to solve the problem until it appears, but you know, once it appears, it could be a really big deal. So quantum key distribution is one way to overcome this, because what you do is that you use quantum mechanics in order to establish a key that can be verified to be secure. And since it's based on physics principles, there are no assumptions about computational difficulty or anything mathematical. So it's really based on fundamental laws of physics. And there's a lot of work going on in that area to commercialize and develop such systems. And we'll talk a little bit about that also in the rest of the talk. Okay, there's another application of quantum networks, which is on quantum computing. So, you know, when people build quantum computers, we can think about, let's say, put it this way, once in a while we had computers, maybe 30, 40 years ago, that weren't connected to the internet. I think today it's hard to imagine a computer being as useful without being connected to the internet. So it's something that we take for granted now, that, you know, computer and the internet is almost like a combined thing. And in the same way, you know, right now people have ideas for how to use quantum computers, but everything that you can imagine doing on a quantum computer could be potentially even more interesting if you can connect it to the internet. You can, you know, bunch quantum computers together so that you can get a bigger quantum computer by combining several of them in different locations. There are some really interesting protocols for quantum computers over a network where you can have a user ask the quantum computer to calculate something for them without the quantum computer knowing what it's calculating. And only the user, once it receives the result, will find it useful. So this could be, you know, interesting if you want to query, let's say, you know, let's go into the stock market or something like that. You want to know, sort of like somebody from a certain location is interested in buying up a company, and they just want to know sort of some of the key performance, you know, metrics for that company, and want to query a database. So this way they can send this query to the database without the database knowing what is being asked, and then the result comes back, and, you know, they can take a decision. And that, you know, potentially means that nobody will know, or it will not influence the markets and things like that. So there's lots of thought, you know, ideas of how one could use that. And, you know, it's all based on entangled states and the fact that quantum systems are a whole, even though they're split into different locations. So only when you have everything together do you know everything about what you're doing. And the final applications of quantum networks is in what we call quantum metrology or quantum sensing, where there are some ideas for how you can use sensors that are connected in some form of entangled state to increase the sensitivity. And one of the first proposals was actually on how to use that for astronomical observations, where you could show that there was a potential for increasing the resolution of a telescope or a bunch of telescopes if they were connected in some quantum state with some quantum state, right? So we saw on the talk a couple of days ago on the black holes, how connecting telescopes together with a precise clock was enabled you to have a larger telescope. So imagine something like that, but where all of the telescopes are connected with some quantum in a combined quantum state. So those are sort of some of the motivations for building quantum networks. So if now I'll go into a discussion, as I said, on some of the considerations for how to build these quantum networks. Let's see here. Okay, so first thing to mention is how do we connect, how do we exchange quantum information over distances? Well, we want to choose something that carries quantum states really fast and has useful ways to encode the quantum state and doesn't get lost along the way. And it turns out that photons are really great. So the elementary particle of light, because most of us can appreciate that light travels really fast. And again, referring to the talk from a couple of days ago, as we can see photons arriving to Earth that were emitted from, the age of the dinosaur, or even at the Big Bang. So, photons live and travel really fast for a really long time. So let's pick those for transferring the information over the network. That's some no-brainer. And then the problem to choose is then how do we transfer these photons from A to B? And well, there are two main choice ways of doing that. You can use optical fibers, which are used in telecommunications a lot because you can make basically a window through these optical fibers that go around corners and under the ocean. So for very long distances, so they're kind of convenient, but they do have some loss in them. So they have this characteristic loss of 0.2 decibel per kilometer. And that does, could become a problem if you go over really long distances because it is an exponential loss. Then, if you don't want that, you could go into free space, just send a beam of light from one place to the other. Of course, the problem is that you have to go in a straight line, and that's not always possible. Most of us believe that the Earth is round. I'm watching a lot of flat Earth videos on YouTube, so it's kind of fun. But the majority of people do agree that the more boring assumption that the Earth is round, and so so that's a problem in itself. And then you have other things that could cause loss, such as turbulence and absorption in the atmosphere. So it's not simple. We'll see that, the key application of free space quantum networks is really when you don't have turbulence and you don't have atmospheric absorption, which will be in outer space. So that's where, free space quantum communication really can kick in, but we'll come back to that. So those are the things that have to be considered when you're talking about distances. How does these channels behave? And then based on that, we'll try to develop some notions about what we choose. Okay. Right. So here's, for example, for direct, if you're on a short distance, sort of, let's say you're less than 100 kilometers that you want to transfer, then you can plug in the loss from an optical fiber, and you can see that over about 100 kilometers, you get about 1% of the light through. Okay, that's reasonable. You can live with that. It's still decent if you send something at 1 gigahertz of a clock rate of your signal. You're going to get 100 megahertz. That's still pretty useful, I would say. So in that case, you can just directly transmit photons or the light or the signals through an optical fiber on that scale. So this is the first length scale we're going to talk about, is the one where we're sort of within what we could call a metro area of a city, or sort of a region, a smaller region. Okay. So lots of experiments have been performed just using, obviously this is the simplest thing to do. So, this is where a lot of experiments started. We have, back in, several years ago, this is probably more than 10 years ago, we had quantum key distribution done between different locations within Switzerland. And we have teleportation being done. This is our teleportation experiment within the city of Calgary that we did in 2016. And, we also have something where you could distribute sort of these complicated entangled states. I haven't really defined what that is, but, all kinds of things that people have done. This is actually over an undersea optical cable between Sicily and Malta in the Mediterranean. So lots of things that you can do as long as you stay, your here is 96 kilometers, you stay below or around 100 kilometers. I would say these days with some really fancy protocols for QKD, they pushed it all the way up to like 400 or 500 kilometers, but that's sort of very low rates then and not very efficient, but it can be done. Let me just take one step back and make sure that we're on the same page when it comes to what quantum information is. And we'll use some of these states here now in our discussion. So this was a slide actually from the tutorial yesterday. So just as a reminder, when we're talking about quantum information, typically what we mean is we're encoding information into bits that are in a quantum system. So we call them quantum bits or qubits. So for example, if we have a polarization, we can have two orthogonal polarizations that can be vertical or horizontal, or we can also have another basis for encoding our polarization, which can be diagonal and anti-diagonal. And so those are both valid bases in the sense that they're orthogonal to each other. So if we measure one, then we can know that it's not the other state. But the interesting thing is that if you're looking at this diagonal basis, it's actually also can be seen as a superposition of a horizontal and a vertical photon. And so in the interpretation of quantum mechanics, that means that if you were to measure this photon in a basis which is a horizontal, or you were to ask this photon, are you horizontal or are you vertical, you'll have a 50% chance of measuring one or the other. This factor of 1 over square root of 2 is the probability amplitude. If you take the square of that, so that will be 1/2, you get the probability for measuring whatever the different outcomes are. Here, the square root of 2 is shared between both of them, so it's just the same front factor, right? So basically, the idea is that whenever you have quantum systems, they can be in a superposition. And if you look at the number in front and you take the square of that, you get the probability of measuring it to be in that state. And so that's an example of the polarization basis. We're also working a lot with what we call a time bin qubit, where we have the probability of a photon being either arriving at an early time or a late time. And then you can have these superpositions of the photon being either early and late. And you can have a different phase between the two, which basically depends on the slight, on the scale of the wavelength of the photon, whether it's displaced by pi, an integer number of wavelengths or an integer number of wavelengths and pi/2 wavelengths, right? So it's just a little displacement and it gives you this minus here. So it's a complex phase. So these are sort of different ways of encoding quantum information. And so when we send photons over an optical fiber or a free space link, well, what we're first doing is that we're encoding the information in some way. So we're preparing, let's say, this photon to have either vertical polarization or horizontal polarization or some superposition. And then we send it over, and then, whatever you want to do, somebody measures it on the other end or something else we do with it. But it carries this quantum information or this qubit. Okay. Okay. All right. So let me, and so I'm going to jump straight to this because we did talk about QKD yesterday, and I'm sorry if for those who weren't there yesterday, I apologize, it may be a bit of a jump now, but one of the things we talked about, and this is relating to the research we're doing, that quantum key distribution systems or QKD systems do have some vulnerabilities. If you're implementing a quantum key distribution system, The principle behind it, the sort of the physics behind it may be correct, but you are making some assumptions on how the detectors and the different devices work in your system. And if somebody can come in and hack those devices, then they can circumvent the security that's guaranteed by the physics. So we call those kinds of attacks side channel attacks. So you can imagine, as a simple device that nobody actually tries to intercept the quantum signal, but somebody puts a little antenna outside of the measurement device and tries to detect the electrical signals depending on which of the detectors that click. And then they basically know what the measurement result was because they've figured out some radiation that came out from the detector or similar things like that. So there are ways to think about these side channel attacks. Okay, now the detectors are obviously the most vulnerable because when you have, when you think about a quantum key distribution system, the detectors are the ones that have to allow light to come into them, right? If the transmitter, the one that sends the photon, you can put sort of an optical diode in front and you can prevent light or anybody from accessing it from the outside. Basically, everything is outbound, but the detectors have to accept information or something from the outside. So if you want to hack, it's the easiest point of hacking. And a lot of the sort of the demonstrated side channel attacks have been on the detectors. So people came up with a protocol called measurement device independent QKD. It's sort of a bridge between fully device independent QKD, and it's one where you don't have to trust the operation of the detectors. And the way it works is I'm not going to go into too much detail because it's going to be quite a lot of math, but what you have instead of in traditional QKD, you would have an Alice sending the photons to a Bob, A to B. In the MDI QKD, you have a third party, which we call Charlie here. And this person measures photons that have been sent by both Alice and Bob. And what they do is that they project it onto a particular state, which establishes a form of correlation between Alice and Bob. So initially, Alice and Bob send some qubits to Charlie, and they don't know sort of what each of them sent. But then Charlie does a measurement. You'll see here that photons come in from both sides and meet on a beam splitter. This beam splitter mixes up so that afterwards you don't know which side the photon comes from. And then if you detect a certain pattern in these two detectors, these are single photon detectors, SPDs, then there is a knowledge of how these two were correlated with each other. Typically, it will be so that they know that they're opposite each other. So what Charlie does is that he tells Alice and Bob, okay, I measured this. And then they know that they sent the opposite qubit as long as they use the same basis. So there's a, similar to regular QKD, there's a loss of half of the data because different bases were chosen. But in this case, it's to prepare them. We'll come back to what kind of measurements this is when we talk about quantum repeaters. They're actually, this measurement is to measure them in what's called a Bell state. And Bell states are the maximally entangled states. So from one way, this MDI QKD is the inverse or the time reversed version of the entanglement-based protocol that Tony Leggett was presenting. So there you had an entangled source sending out entangled photons that are being detected. In this case here, we send photons to a measurement station. That measurement at Charlie projects those photons onto what we call an entangled basis and sort of creates a time reversed entangled state. And the point is that this only works if at this beam splitter there is a single photons interfering. So if you try to intercept this anywhere, you're going to destroy that quantum effect on this beam splitter. So even though you're measuring with the detectors, actually it's this beam splitter that kind of does the quantum part of it. And so that's why you cannot interfere with it, because you'd have to emulate a quantum measurement or do a quantum measurement, and that you can guarantee cannot be had. Okay, so this is some little bit more advanced. These are the detection patterns one is looking for, but and then let's not dwell too much at it. But here's sort of the kinds of graphs that you'll see when you look at people doing QKD. It's the secure key rate as a function of the loss in the channel. The more loss you have, the less signal comes through, and you're assuming that your noise is constant, so your signal to noise ratio decreases. You have more and more errors. The more and more errors you have, the more error correction you have to do in order to retrieve faithfully the signal. And at some point, you cannot error correct anymore. You reach this 11% limit that we talked about yesterday. And then, there's just a cliff here where the key rate cannot be positive anymore. It goes to 0. If you go above 11%, then you basically have a negative key rate, which means that you can't basically get any secure key anymore. So this is an example of how you would plot that. Okay, now let's see what I have on the next slide. All right, so here's an example of okay, so here's, a summary of what I was saying, some of the advantages of this MDI QKD setup. Here's an experiment which was done in the group in Calgary before I joined, or well, I think I was there, but I wasn't involved in this particular experiment, where they did this MDI QKD protocol between different locations in Calgary. Here, Charlie is at the university, and Bob is at the hospital, and Alice is at the Polytechnic in Calgary. Another thing that I didn't mention here about this protocol is that when you're looking at it for a more sort of like commercial perspective, it's an advantage that you have these single photon detectors here, which have to detect the single photons, the qubit states, at a central station, because you could think of different users actually using these detectors. So you could have Alice 4, 5, 6, 7, 8, 9, 10, all using the same detectors, just with a switch connecting to them. And these detectors are really the most expensive part, because they are, to work at telecom, they are these superconducting nanowire single photon detectors. Here is our array of those detectors in the lab. And, they're on a nice gold plate. And that's because they're actually inside a cryostat, and they have to be at 0.8 Kelvin to work properly. So, all of that, it gives you an overhead cost. Right now, you can purchase these guys commercially for about $15,000 Canadian, and sort of something like that, 12, 13,000 US. And the cryostat is about 100,000, right? So, it costs a little bit, and it's good if not every user has to have that. So that's another advantage of this kind of architecture. Another thing that is important to think about when you're talking about quantum networks and QKD is, the cost of the detectors is one. The other thing is the cost of the fiber. So optical fibers, they're typically controlled or put in the ground by telecommunications companies. And if you ask them how much it costs to rent a fiber, you'll find out that it's actually not that cheap. So if you wanted to isolate that fiber just for yourself, well, you would have to pay quite a hefty price. So one of the important questions people have also been trying to investigate over the last couple of years is whether you can have the quantum signal coexist with other communication in the fiber. That's a very interesting question, because you have to remember that the quantum light is at the single photon level. So that's really, really a very, very small power compared to classical communication, which operates in the microwatts or milliwatts, which is billions of photons. Of course, the one key thing that you can take advantage of from telecommunications is that at the same time, through an optical fiber, you can send signals at different wavelengths. This is called wavelength division multiplexing. And so you can think of just putting the quantum signal in another wavelength channel and then filter away all the rest, right? So here's an example of sort of the notion of that. You have a quantum signal here. The quantum signal is created by Alice and Bob here, combined with some classical signal going over fibers. And then here it's split into the measurement station here, and the classical signal is just amplified to go continued back and forth over a different wavelength channel. The problem that you experience here, and the key effect that makes this difficult, is what's called Raman scattering. So this is where photons at one wavelength combine with a phonon, that's a vibrational state or a vibrational excitation inside the fiber, and creates a photon at a different wavelength. So basically, it's sort of like a wavelength conversion thing that happens. And so if you measure it, for example, here, we had a measurement done here where we have our quantum channel here, and then we put a classical light at different wavelengths and measure how much actually goes through at the quantum channel. We see that we have these bumps here of where light is created from that other light and going into the quantum channel. And of course, there'll be noise, right? So now you have photons that have nothing to do with the quantum signal that are being generated. So one has to carefully consider what kind of wavelengths can you use for the classical and for the quantum communication without disturbing one. And so we had a paper out on that where we characterize that. And so this is the the whole system here, and there's a lot of details which I probably can't go into, but I'm happy to discuss a little bit about all the different components that go in there into the measurement. So those are just some interesting questions and studies to be done when you're trying to do quantum key distribution, some relevant issues to consider. So I'm probably going to skip this. So right now we have a project to develop sort of commercial grade MDI QKD system in the lab. And again, this is just to show sort of some of the complexity here we're working on. We're aiming at having a 200 megahertz clock rate. We want to use these superconducting nanowire single photon detectors. We want to use a field programmable gate array to be the brains of the whole operation and to do the controls and the analysis. And so here's sort of our current working schematics of that, where we have an FPGA controlling a whole bunch of peripherals that create the signals at Alice here, and here at Bob we have the detection, and then we have some analysis of the signals and some communication back and forth over optical fibers. Again, not the details are not important. The more there right now is that this is sort of the almost an engineering problem we're working with, and some of the students actually, the postdoc that's working on the FPGA is an electrical engineering background, and I have a communications engineering student working along with another engineering student working on this. So we're actually we're sort of transitioning into the engineering problems here of constructing a robust system, but of course the underlying physics is firmly quantum mechanics, but there's a lot of practical considerations to go. So I thought that that's something that you guys will like here. Okay, so let's see. So now we've been talking about these relatively short distances, the intermediate distances. And it turns out that one can do an analysis of how much information can you send over a link. Which only depends on the loss of the link. So people did some studies. One can say that the QKD protocols that we developed may not be the most efficient ones. Maybe there's some smarter way of doing it. But it turns out there are some theoretical bounds to how much information you can carry over an optical fiber or over a link more generally. Sorry. So there are these, this is the bound that's described in these papers, and here is the orange line defines that bound. So basically here is the probability of getting your qubit through the link, and it goes towards unity for 0 distance here. And this is now assuming the loss that you have in an optical fiber. And you can see that, we have the different protocols. We have the BB84 that we discussed yesterday. We have our MDI QKD protocol, and both of them are underneath that line, showing that, they're maybe not optimal, but they're close to the bound that you can get through such a channel. The problem with that is that it's an exponentially dropping curve, which means that at some point, you're going to have a ridiculously low probability of succeeding when you go to long distances, and you basically should just give up because there's no point in doing that. And then, physicists don't like these kind of things. They say there's got to be a way to solve this, and of course there is. And people have come up with a couple of different solutions, in order to overcome this limit. And that really points to the distance question. So, now we've solved quantum communication and quantum networks for short distances, but we can't go long distance. So we have to find a way to get to longer distances. Okay, and I'm going to go through 3 different options for how to overcome this. Okay. Oops. Yeah. The first one, call it solution number 1, is a little bit of a cheat, because what you do is that you basically break up your quantum link into some distances which are manageable. So let's say 100 kilometer long. And then you insert a station where you decode the information into the classical world. And then you can, amplify it or make sure that it's secure. You can basically analyze it at each of these nodes. And that's why it's called a trusted node network. Trusted because, well, it's important that that person, once it's gone classical, it's not secure anymore. And so that person has to be trusted. That means that every 100 kilometers, you have to build a little fortress and make sure that nobody can invade that or get any information about that. It does enable you, to set up a system that can span, any arbitrary distance, because you are only putting it into these short links, relatively short links. And it's an approach which has been followed in a couple of places. Most notably, it's been followed in China, where they have since several years ago. So 2017, they made this link between, it's a bit hard to see here, but between Shanghai and Beijing, that was about 2,000 kilometers long. And it has 32 trusted nodes along the way, but it works. And partially, I guess it's, a government sort of push to develop this. And so it's funded and government companies are encouraged to use it, but it exists and they're expanding it. So here's their plans. They want to build a little link here to Wuhan, and then they want to build this long one from Beijing down to Chongqing, and then all of these yellow ones potentially. Who knows if that's going to happen, but that is, one way to overcome it. And we have also here in the UK, they're building something like that. But as I said, the problem is that it's not really quantum all the way. And one of the problems, as I said, is that you have to trust the nodes. And secondly, is that you're not actually able to do everything for a quantum network. If you're decoding the quantum information into the classical realm at every single node, you cannot, for example, distribute entanglement between 2 different nodes. You can do QKD, but that's about it, right? Because you have to be able to, you cannot actually share an entangled state that way. So it's limited in terms of the applications, and it's also, potentially insecure. Somebody just has to hack one of those intermediate stations, and then you have a problem. So that's solution number 1, which was a little bit of a cheat. But the solution number 2 is to change the loss. So when we were plotting this graph before, we're plotting as a function of distance, assuming a certain loss. But that loss was based on the exponential loss in an optical fiber. And as I alluded to before, there may be better ways to send the quantum signal over long distances than through an optical fiber. And the obvious choice is to do it in vacuum of the free space. So in that case, we can ask ourselves, what is the loss scaling of such a signal here? And so let's say that we have a beam of light that we want to send over a really long distance from A to B. And what is the kind of loss we're going to get? Well, it's going to be limited really only by the fact that all beams have to expand. There will be a finite divergence angle of any beam. So you guys are all in some of you have had optics, I should say. And so you might be familiar with Gaussian optics, where that depending on the initial size, there's going to be some expansion angle, right? So it can be very small, but it's going to be finite. And if we're talking about thousands of kilometers, it can be a significant increase in the size of the beam. So let's say we start out with a beam with some divergence angle here. And then, you know, as it travels here, distance L here, it keeps getting larger and larger. It has some radius, which is just linearly proportional to the length we're given this angle, right? So that means that the area is going to grow with the square of the distance. At the same time, at the receiver, you have to detect this signal, and you're going to have some size of your detector. It can be a telescope, but you know, it has a finite size. And that's what we here have defined with the radius of the detector. So if you look at then the fraction of the light that you're detecting, given that the beam is continuously expanding, you can get this sort of loss function here. And basically there's a 1 here, which indicates that if the beam is smaller than your detector, you're detecting all of it. And then once it gets bigger than your detector, you're going to get this kind of scaling here. So if you look at comparing, you know, this BB84 protocol in vacuum versus in an optical fiber, you see that, well, we have the initial good, everything is detected. Then we have a sharp dip where we actually get worse. But then at really long distances, you can see that there's a huge gap here on the exponential scale. And that's the key behind why free space quantum communication works so much better, as long as you don't have any absorption by the medium that is traveling in. Yeah, and why that's a good solution for really long distances. Now, as I said, you know, you can't, it assumes vacuum, and the vacuum that, you know, is the most accessible to us over such long distance is the one that's in space. And again, we're going to head over to China because they decided to put I shouldn't say bad things here, but a shitload of money through into this and just launch a half-ton satellite with just about everything you can imagine to put into it. So this was done in 2016. It's a low Earth orbit satellite, and it's called Micius. You know, they were able to demonstrate, you know, a link between different locations within China and also one to Vienna. The group leader in China, he did his PhD in Vienna, so that's why they have good links there. You know, that generated a whole bunch of interesting results. They also had an entangled source on the satellite, and were able to demonstrate entanglement between 2 different ground stations that was transmitted with a distance of 1,200 kilometers. So if you were to do that with an optical fiber, you would have to wait a lifetime to get the signal. But because most of this transmission is in vacuum and free in space, it works very well, and you can go span these large distances. Okay, and so there was other, you know, lots of other papers coming out around this kinds of experiments, and yeah, they had this video conference, presumably between Vienna and China, using this satellite. Now, we like this because it's a nice way to connect, you know, the small distance fiber networks to the large scale fiber networks. And so here's what we have. This is actually from the edge of campus in Calgary. So this is our ground station. And this little spot up here, which is green, that's actually the Chinese satellite shining its beacon light down to us. So the way that such a satellite pass happens is that, well, we have our ground station here. The satellite's going to fly over, and then at some point here, we're going to have a pre-programmed flight track. You know, you can look up any satellite and you can basically program a telescope to follow the satellite. So we pointed in that direction. In the same way, the Chinese space agency have uploaded the file that says where our ground station is so that the satellite can point down to us. Then when we reach some 5 degrees above the horizon, the satellite turns on a green beacon laser. We have a red beacon laser. And then they try to find each other within a camera, and then they have some alignment procedure that they center this green beam and the red beam. And then we're actually tracking each other with different feedback systems. And then in this case, the satellite is going to send down quantum signals to the ground station. And I think here's an example of that. So here's a diagram of how the ground station looks like. So as you can see, here's a big telescope. Where we collect the light. We collect both the green light, and the purple here is the quantum light that's collected. They go into a system here The green light goes on to a fine tracking camera, which tries to align on a very fast time scale the pointing direction of the beam that goes in. And you can see it's shared with the quantum light here in the purple array here. And so there's a little mirror here which can tilt and fine tune so that the quantum light goes into the optical fibers eventually here to the detectors. Before that, we have like a beam splitter and some polarizing beam splitters, and that basically allows us to detect the polarization state of the incoming photons. So this particular satellite, and this link here uses the BB84 protocol. You know, here's an example of the detectors. There's like a halfway plate here that we can rotate, and we can see from a light source where do the which detectors detect the light, and we can see there's, you know, they're in phase and out of phase corresponding to the different bases. And then, whoops. Another thing is to synchronize the light. So where the satellite is flying far away, and we have to know exactly which qubit was sent at which time. So it turns out that this green laser is actually pulsed and creates like a clock signal that we can synchronize to. And then here's an example of the sort of the pattern. It's actually quite interesting. The pattern of the clock signal here, the time difference between subsequent ones is not constant. And that's actually used to match up the patterns between what they say they sent and what we received in order to align the two clock signals. So it's actually not done in sort of real time, but done after the fact. And then here we have sort of the quantum signals. It's a bit small here, but every blue dot here is where we expect the quantum signal. Sometimes we don't get it, and sometimes we have more, but then most of the orange ones here indicate where we actually had a detection from the satellite. Okay, so that's how the synchronization is done. Here's an example of the kind of data we get. So again, here are the 4 different detectors. Here are the signals that we get into it. Here are the number of counts we get per second in hertz. So, you know, we get up to, we actually get some more some other days. It depends a little bit on the conditions, but, you know, 3,500, 4,000 counts. And here's the error rate that we detect. So we can compare with what they send, and then we can say, what was the error rate? And we see, of course, when we have more counts, we have the lower error rate. And when we have less counts, we have more noise affecting it, right? So we're still working on getting the error rate down to an acceptable level. It's a little bit high still, but we're almost there. And we have regular nightly passes. Students have to get up like at 2 a.m. to see the pass because that's when it flies over. We had some issues recently and we couldn't figure out what it was. And it turns out that one of the problems is that during the summer, the satellite, while we're still detecting light from it, is actually partially illuminated by the sun. And that's a problem because then we get sunlight reflected off the satellite, and we couldn't figure it out what was going on, why we had so much noise. And I think it's because we're one of the northernmost ground stations that they work with. So it's a problem that especially gets, you know, around the poles. So a little bit of an annoying thing because usually it's nicer to work in summer where it's not freezing cold. So our long-term goal for the ground station is also to be ready for the Canadian quantum satellite, which will be launched in 2023. It's called KeySat. It's led by the University of Waterloo, but we're one of 3 official ground stations for this satellite. And we'll have to do some modifications. Specifically, that satellite is an uplink satellite, so it will receive light instead of sending light. Ooh, my goodness. Right. All right, another way then to, so this was solution number 2. We're going to go to solution number 3 of how to do quantum networks. And this is sort of the most complicated one, where you don't change the loss, but you find some very fancy way of overcoming the loss in the optical fibers. And this is called a quantum repeater. So for those of you who know a little bit about telecommunications, you may know that, you know, in telecom, signals being sent over long distances rely on repeaters, which are just basically amplifiers. But remember the no cloning theorem, you can't amplify quantum states because that's a copying. So can't do that. So you have to do something else in order to kind of amplify or do a quantum repeater, for quantum signals. And it's a very ingenious protocol. And so here, here's the original proposal, and here's a very, very comprehensive and good review of the protocols. So what it relates to, or what it relies on, is something called entanglement swapping. And I'll try and go through the protocol here and highlight why it works. Okay, so, oh, sorry, I see small animations. Okay, so what you start out with is you start out with some entangled states here. You have, so this is what we called, if you want to have like two users, A and B here, and they want to share an entangled state with each other, they start out with having each of them an entangled state. So we call that the psi minus. Here is a kind of writing of an entangled state. I think I'll have it defined on the next, on some of the slides, but that's one of the Bell states. And so they each have one, so B and B, that labels the two different photons here, and A, capital A and small a labels the photons here. So they start out with having locally some entangled states that are generated from some sort of entangled photon source. The next step is then that they will send the capital photons there into quantum memories to be stored and just wait. And then they'll send the lowercase photons here over a channel to a Bell state measurement. Okay, and here are the Bell states that will be measured. So this detector here will determine whether the photons A and B were in one of these states, whether they resulted in one of these measurements. I think there's, yeah. So actually, if you look at the combined state of all the systems, so here we have the two initial quantum states of the two different nodes here. And if you just multiply these states, so these are psi minus states, so that's the one with the minus here. If you multiply all of that together, you can show that you can decompose it, instead of in terms of the A states and the B states, you can write it as the capital states and the lowercase states as this sum of four different terms, right? So it's just really rewriting this into a different expression by just multiplying and then separating states into this kind of pattern here. So what that shows you is that if you're measuring here these four states, and you look here, so that's the lowercase states, this, it means that if you're measuring this state, for example, you know that the photons that were in the quantum memory must be in this state. And similarly, if you measure this one, you know that they must be in this state. So by looking, going back. Okay, so by looking at the measurement outcome here at this measurement station, you can actually create an entanglement between these photons that are stored in the quantum memory. You know, because that's what quantum mechanics is. It's like you start with some state, you don't know it initially, can be any of those, but once you've done a measurement, you can then say that the wave function collapses and becomes compatible with only the one that corresponds to the measurement. And that means that these two photons, even though you didn't measure those, can be verified to be in this state. So now what you have is that you have created entanglement between the photons that are stored in the quantum memory. Okay, typically one measures one of these two states because there's there's some limitations when you use when you don't have a quantum computer, how many of these states you can distinguish here at this measurement, but that's a more complicated issue. So you have like half of the time you measure, you're able to measure something that's useful. Okay. So now we can ask ourselves, what is the rate of distributing this entanglement? Well, okay, so we say that the whole link here has some loss. We call it eta. We have some clock rate at which the experiment runs. We call that gamma. And then we have some efficiency of the quantum memories. Here we have two of them, so that becomes squared. And then this 1/2 comes from the fact that we can only measure half of these states at this measurement station. So this is going to be the rate at which you're distributing entanglement. So you can increase, you know, the rate, and of course it will go faster, right? So this is the one link, right? So now we're going to make it more complicated. We're going to look at, well, the problem of connecting A and B when the distance is very long. We're going to split this distance into, well, let's start with 2 links here, but then go on to the principle of longer links. And then what we're going to do is that we're going to build that setup that we just shows for distributing entanglement but double it twice. So we have one of these, what we call elementary links here, and we have another one here. Yep. And what we see is that they're connected to each other in the middle here. So we'll get to that in a second. All right, so what we do here is that we'll distribute entanglement over one of them first. Whoops, there we go. And we say that we have, now we can create entanglement between different links like this. So we have entanglement distributed between these two quantum memories and these two quantum memories. And then we can combine by releasing the photons from these quantum memories onto this measurement. We can sort of make entanglement again over a full link. So we've done it sort of stepwise distribution of entanglement. And what we're going to talk about then is like, what is going to be the rate of that happening? Okay, let's see here. If we just do it naively here, well, we've taken the loss of the entire link, and then we split it into n sections. So here I've drawn 2, but in principle can be n sections, capital N. So that means that the loss is just the square root, the nth root of the total loss of the link. Of course, that's going to be smaller. Then we have the same 2 quantum memories each time, half the probability of 1/2 of creating the entanglement. And then we have this n here to the power of n because we have n of these links. Right. So right now there's no advantage because this n just cancels this n, so there's no advantage here. And then the rest is just the fact here we have a 1/2 to the power of n minus 1 because every time we have n minus 1 these connection links between them, and they have a 50% chance of succeeding. So that's why we have this factor, and then we have the clock rate. So this is if we just tried, naively to do this. This is actually called a quantum relay, and of course there's no advantage to it yet. So we have to do something a little bit smarter. We have to look at the success of the individual links occurring, and that's each of the elementary links. So this is the probability without the power of n of each of them succeeding. So if we put that in here, and then we look at what is the probability of it not succeeding. That's of course 1 minus this factor. And then let's say that instead of trying just one time, we're allowing us to give it m tries. So there's this little m here, and we say we're going to try to establish this entanglement maybe 10 times or 100 times. Then the probability of succeeding in 100 times is the probability of not succeeding to the power of m. Oops. The probability of not succeeding to the power of m, and then 1 minus that. That's how you would calculate the probability of succeeding if you give it m tries. And then you have the same rate here, but you have the rate divided by m because, of course, you have to have time for all of these. So you can only, your clock rate gets reduced by that factor. But that's a very different kind of scaling. Basically, you can, by making this m large enough, you can make this go to unity, this whole factor here. So you can basically make a unity probability of succeeding over one of the links if you just try enough times. And then you don't connect the links with each other until you know that it succeeded here, and you do the same thing over here. So the point is that the Bell state measurement here will tell you when you succeeded. So this is why quantum repeaters work is, you have a herald, an announcement of when you succeeded, something that you cannot do if you were to just transmit the photon from A to B. And the other important thing is that this Bell state measurement does not measure individually the state of the photons, because then you would go into the classical world. The whole point about the Bell state measurement is it measures jointly some property of the two photons, but not individually the photons. And that's why you're allowed to do this heralding measurement and still maintain the entanglement. So lots of interesting quantum mechanical concepts in this particular protocol, and it's very, very neat. So now if you go to analyze what is the rate of distribution when you have n links, you just take this whole expression, except this factor which stays the same, but this thing in the bracket here in the parentheses, and it's put it to the power of n. But now because you can saturate this to 1 to be closer and closer to 1 by just having m large enough, this is going to be able to be better than just direct transmission. You still have this factor 1/2 for all the n to the minor power, n to the -1 for all the interconnects. But this is now the rate of distributing entanglement when you're using a quantum repeater. And here's some plots. So if n is equal to 2, for example, you can try with different numbers of attempts. And you see that, of course, in the beginning here, for short distances, if you have many attempts because of this division here, the rate is going to be slower and slower, right? Because you're slowing down your whole protocol by forcing it to try many times. So it's easier just to, not do it and or have fewer attempts. But once you go to a certain distance, you see how the lines cross. And, here we have 300 kilometers. You see that the more attempts is better. So you end up actually being, better off because you're trying to saturate this thing inside the parenthesis here that goes to the power of n towards unity. And you can also look at it from another point of view. You can look at it and say, let's have a fixed number of attempts, but let's insert different nodes. Then, of course, the loss here goes towards being smaller and smaller for each of the nodes. The square root, the nth root becomes more and more smaller and well, actually greater and greater. And so another way of saturating this towards 1, we see the same kind of behavior. Initially, the fewer links is better because you have all these lost terms every time. But as you go to longer and longer distances, you see that splitting it into more and more links is going to get you towards a better and better rate. And this particular protocol then circumvents some of the problems of the long distance. But as you will notice, it relies on a whole bunch of things that are complicated. We have entangled pair sources. We have these measurements, the Bell state measurements over long distances. And we have the nastiest of them all, the quantum memory. So let's see where we are. Okay. So I'm not going to talk about the multiplexing part because I want to talk about memories a little bit. Okay, so just to note that, there was an experiment, some experiments done for demonstrating this, what we call the elementary links, actually last year. And I was a referee on these papers, so I got to know them fairly well. One in Spain and one in China, where they demonstrated in an elementary link for the first time. And so, I'm not going to explain these too much, but this is basically a way to show that the input and output quantum states were the same. This experiment in China was the one that was sort of closest to a real repeater and sort of more technical stuff. But for the whole measurement, for the data, they measured a total measurement time of 160 hours over a month. So to get this data really still is very, very slow. This protocol that they did in Spain was faster, but had some things where you'd have to modify it a little bit to be really useful. So things are being done. And the interesting thing is that for the quantum memory that was used in these experiments, they all used a very specific system. Okay, so I'm going to briefly go through what we want for a quantum memory. So quantum memories, what you want is you want them to be efficient, of course. You don't want the loss to be in there. You want the storage time to be long enough that you can communicate back and forth between your nodes. You want the fidelity, which is basically how close does the quantum state that comes out resemble the one that was sent in. You want that to be high because otherwise you change your quantum state, you're going to have errors. You might want to have it at telecom wavelengths if you're using optical fibers. You want it to be able to store multiple photons at the same time, multimode storage capacity, because that increases the rate in the quantum repeater. And then something that's sort of like more technical is you also wanted to have a large bandwidth, because basically if the frequency acceptance frequency range of the memory is large, then you can store really short signals. And if it's very narrow, then the signals have to be very, very long. So they have to be spectrally very narrow. And that means that, the rate at which you can run your experiment has to be slow too. So it really is an important consideration, but not something that everybody who's building quantum memories is considering. Okay, what we're doing is that we're basing our quantum memories on rare earth ion doped materials. So what are the rare earths? They're down here, the lanthanides. And we love a couple of them in particular, thulium, erbium, and ytterbium. What are rare earth ion dope materials? Where rare earths sit inside some sort of crystal lattice here. The crystal lattice is never really perfect, so you have some distortions. That means that each of these transition lines of the rare earths gets slightly displaced, and it causes some inhomogeneous broadening. So it basically means an atom has a well-defined transition frequency, but it's different from its neighbor. The rare earths have some very good properties. You know, they have lots of different optical transitions in different wavelengths, depending on which one you pick. They have very narrow homogeneous line widths. Oops. Which means that you can interact very reliably for a long time with them. They have large inhomogeneous broadening, which means you can make them very broadband. So you can have a very large acceptance range for your incoming signals. And then, you know, the coherence time, so basically how long do these quantum states stay neat, can be extremely long for especially spin levels that exist. So, you know, hours, or some of the more recent results even show days long coherence time. So really impressive stuff. And lots of people are researching this as well around the world in the rare earths. There might be a few more. I always say that we have a unique Canadian advantage when it comes to these cryogenically cooled systems, is we just do it outdoors. So I'm going to try and get through the protocol here just to show what we're doing. So here is what we have. Let's say you have a photon here, and you have these two levels here, and a ground state and an excited state. So this is an optical level. Here we have a single photon coming in. And, you know, here is sort of the frequency spectrum of the photon. So it has some distribution limited just by the width, the spectral width of it. And then we have atoms here. They all have different wavelengths because they're inhomogeneously broadened. So these are like a collection of different atoms. If light comes in, it can be absorbed by this collectively by these atoms. So if you look at it like here, we have the input state, the quantum state is one photon, and all the atoms in the ground state, right? Because that's where they start out. Then if they get absorbed, then this photon goes to zero. So it's like a zero photon state. And then we have an excitation of one of the atoms, but we don't know which one. And it could be any of them. So we'll have to write, the way you deal with that quantum mechanically when you don't know is that you write all the possible possibilities down. So this is just not normalized, but basically what you have here is that you have a sum over all atoms where one of the atoms in the excited state and all the others in the ground state. Okay, so that's a sum. And then you have this phase factor here, which takes into account that they're at different frequencies with respect to each other. So that means that each of these terms in that state will have a slightly different phase, which will evolve with time and which depends on the exact frequency that it has. What you can then do is that you're relying on at some point the phase initially was zero. Oh, okay, so I think I'm missing. No, this has to be here. Sorry. Wondering. Anyway, so let me. So now we have this absorption, this state, right? What we then do is that we modify our system a little bit. We take and invoke a new level. We call it just a shelving level. We call it, where we can put some of the atoms into it. Then we first, before we send in the photon, we create this row of peaks of absorption lines where we've removed some of the atoms. There's a little bit of background left, but we have these peaks that are separated spectrally by delta, some frequency. And then when you look at, and so these atoms will be in some metastable state where they can stay for a while. Then when we absorb the photon now, we see that instead of having a whole bunch of frequencies possible, we have only a certain integer value separated frequencies that are possible. So this M here is an integer, and this delta here shouldn't have an ion, it should just be a delta, but you have these discrete levels. That means that the phase of the state evolves like this with time, and delta being the same for all of them, and M being integer. So if you plug in a time t here, which is 1 over delta, you'll see that this delta goes away, and what's left is just 2 pi m, which is an integer. And that means that the phase of this state at this time becomes an integer multiple of 2 pi. Now, if you know anything about complex functions, an integer multiple of 2 pi is the same as 0, because you go back to the same spot. So basically, you've recreated the state that was there when the photon was absorbed. And what then happens is that the photon gets emitted spontaneously through some sort of super radiant effect. Basically, you have a macroscopic sort of like alignment of all the dipoles in the atom. And so you get this re-emission of the state where all of the atoms go back in the ground state, and we have a photon coming out. And that's why we call this kind of memory photon echo memory. So this is the basis of the protocol. So you have an input and then the re-emission after some fixed storage time 1 over delta. Here's a formula for the efficiency, which is a little bit complicated. And let's see. How much time are you giving me here to to spend? I just want to make sure. You guys have a talk at 1:30? Oh, I have until 1:30 or 1:15. Oh, I thought it was like 5 minutes over time already. I was getting really nervous. Oh my goodness. Okay, so I have like 25 more minutes. Okay, excellent. We have 15 minutes for questions, right? Excellent. Oh, whew. Good. That's good, right? Because I really like, so the reason I should say that, when I came to study, so I was doing my PhD in sort of more quantum optics related to clock transition and spin squeezing, but I really loved rare earth memories, and I thought this is the cool thing that I want to work with, and so this is the thing that I like the most to work with of all the things, and I really like these memories here. So I'm happy I can get to discuss a bit more about them. Okay, so a couple of interesting things that we looked at, and this is an idea by some of our theorist friends, is that when you look at this state here, that's actually a kind of entangled state. It's called a Dicke state, and it's entangled because if you measure one of the atoms here to be excited, you know that the other ones are in the ground state, and you can tell something by measuring just one of the atoms. So it's an interesting entangled state, but the question is, how many photons are entangled, and how do you figure out how to measure how many of the photons are entangled, how many of the atoms are entangled inside this state? You need some sort of what we call an entanglement witness. An entanglement witness is some sort of metric that allows you to quantify how much entanglement you have. And there were, a couple of years ago, several papers where they had measured different demonstrated or proven that some number of atoms were entangled. Here in 2014, 40 atoms. I don't see this one, how many. Here was 3,000 atoms. And we felt that, because inside such a solid, we have, billions or hundreds of billions of atoms, that we probably have more than that. So we thought that we could try and quantify that. And it also helped us to understand this whole memory thing with a nice analogy to more known optics. So here's the analogy. You can look at these peaks, or this frequency comb that we have in the atoms, as being kind of similar to multi-slit experiments for light. So you may know that if you look at the multi-slit interference here, you have here's a single slit, right? First, you end up with a single slit here. You send in a plane wave, and then you'll have some diffraction pattern here, depending on the size of the slit and the distance and so on, right? And then if you add 2 slits, then you get some interference pattern in addition to the overlying sort of sync pattern from the diffraction. And you'll see that if you keep adding slits to this grating here, you'll start to have sharper and sharper teeth here. We can add, I don't know how many I have. Oops, I have even one more here, 5. And we see that we start to get this pattern with some slits that are separated by some spacing here. And so we can look in a similar fashion, we can understand these frequency combs in atoms as sort of like a multi-slit experiment in the frequency time domain, whereas for like if you had a position, a grading here, you would have sort of like it's sort of like a multi-slit experiment in space versus momentum or angle, because you're changing the momentum or the angle of the output photon where it arrives. So there's an analogy between these kind of frequency combs. Here, what's illustrated is sort of these absorption peaks in an atomic medium, a frequency spectrum of an incoming photon, and then the resulting temporal signal that you get from that. Now you'll notice that this is symmetric around 0, whereas this is not. And that's because when you look at the interaction of the photon with these atomic peaks here, what we're showing here is the absorption of the atomic peaks, but there's the absorption, as you may know from atomic physics, is actually only one part, or can be described as one part of the index of refraction. More specifically, it will be the complex part of the index of refraction. The real part of the index of refraction will be the dispersion of a medium. So that's what typically we think of as index of refraction. But in atomic physics, those two are related. And the way that they're related is they're related with something called the Kramers-Kronig relations. So they're not independent from each other. That means that when you have an absorption profile, you're always going to have some sort of dispersion profile. And if you plug all those numbers in, you'll see that that actually ensures that you only have emission of these peaks after the pulse was sent in. And this points to really the origin of the Kramers-Kronig relation, which is causality. They ensure causality, and you can kind of see that that's what comes out of it here too. All right, so there is this relation, and it's kind of interesting to show, and it also allows the theorists, and there I'm not going to go into details because frankly I'm not sure exactly all of the details of that, to verify using this signal basically how many peaks were involved in generating this pattern. And you can look at it by how well are we suppressing the in between the peaks with respect to the peaks that were emitted. By seeing how big this contrast is, you can see how many of these peaks here, as the same as here, were contributing to the signal, had to be in tune with each other in order to get that kind of a contrast. And that in turn will tell you how many atoms were participating in this collective state that was part of the memory storage. Okay, gets a little bit technical here, but here is this contrast plotted. Here's the experiment, kind of what we did. So we had a source of entangled photons. We use one of the photons just to tell us that there is another photon in the other arm. So this is what I call a heralded single photon source. It's the first kinds of single photon sources were always built like this because it's kind of simpler than more complicated systems based on single emitters. So we just have basically this system ensures that we have a more clean single photon state. We send it into this memory and then just measure the signal after it. And these losses here are just for the theoretical model. You model losses as beam splitters when you do theory. Okay, and here's an example of this frequency comb here with the input profile of the photon. And then here's like this absorption comb that you can see. It's not perfect because you see we have a gap here. So we have some background from 0 to 1, and then we have the comb here. And this is all expressed in optical depth. So how thick optically does the medium look like? How opaque is the medium? Okay. And then we analyzed the height of the peak here with respect to the background that was down here. We calculated this ratio R, and through some math and some calculations that were based on the theorist, we could calculate that we had at least 256 peaks contributing, 256 peaks contributing to the signal. And if we calculate how many atoms that is, that means that we had a total of like 1 billion atoms contributing to this signal. And those had to be in this sort of entangled state. So this was, the highest number of atoms to that time, but that could be shown to be entangled with each other or be in an entangled state.
Okay, so that's, was interesting to just highlight. And also kind of the real thing that we found out was this analogy, which was very useful to see how this, atomic frequency comb can be seen as a sort of a multi-slit kind of experiment in the frequency time domain. Let's go back to this whole experiment here with rarefied solids and the memory particularly. So as you'll see here, I wrote down the efficiency formula here, which relates to, to the spacing between the teeth versus the width of the teeth. So that's what we call the finesse of the comb. So that ratio, the higher the better, but the optical depth also goes into it. So we have to have a high optical depth. The more thick the medium is, the better. And then we also have this exponential loss due to the background residual absorption, so that we really don't want. But if you optimize all of these parameters in this formula to look at the maxima, you still only get 54%. And that's because in this case, when we're sending the light in this way, we're sending the light into the same way and getting it out in the same direction. And that means that some of the photons can be reabsorbed by the medium, and that limits the efficiency that you can get. So there are luckily also protocols that try to circumvent that and improve on that. Let's see if we get that. Okay, this is, I think, the same slide. Yeah. Okay, oh no, I just wanted to, yeah, so let me just first go through the experiments we did some while ago with this, where we used a material called thulium lithium niobate. So it's thulium doped into lithium niobate, and we could actually make these little waveguides. Some of our collaborators did that through what's called an indiffusion process. So anyway, we had these waveguides where we can send light into it and store it. And here's a picture of the kind of frequency comb we did. So you can see, a very broad frequency comb here. All of these are little teeth that go up and down, and it spans over here 12 gigahertz. So that's really, really broad in terms of atomic systems. And it's all due to the fact that we have these inhomogeneously broadened systems. And here's an example of what we see as an echo. We see some of the light being not absorbed and just passing through, and some of it coming out here as an echo. So this is similar to the previous graphs, but here we really see a really nice broad frequency comb. And that's some of the largest or most broadband quantum memories that exist are these ones based on rare earth atoms, and specifically the ones that we have shown. We've also shown similar bandwidth combs in erbium doped optical fibers. So a couple of different systems that we're using. Okay, so the problem with this particular material is that the lifetime of the excited state is 100 microseconds. And that means that you cannot possibly store anything on that transition for any longer than that, because the atoms will decay. And we also can see here that we have a lot of this background absorption here, which just adds negatively to the efficiency. It's just going to reduce the efficiency. So this particular material has some issues, some more sort of like spectroscopic properties, and we want to look for other materials. So one first thing to address is this limit to the 54% efficiency. And you can actually improve on that by putting your crystal inside an optical cavity, where the cavity mirrors must be chosen in a specific way. If you look at the efficiency in that case, it converts here to something else. It's not obvious here, but the limit of efficiency for this expression is 100%. But you have to choose these reflectivities of the mirrors in a particular way. Let's see. So it actually happens so that the front mirror here has to have a reflectivity that is exactly identical to the round trip loss due to absorption of the atom. And the back mirror, you want to have a unit reflectivity. What this puts you in is something called impedance matched condition, where the absorption, basically you can think of it as the fact that when light comes in through the crystal and goes back again, some amount of it will be absorbed, but that amount will be exactly identical to the amount that's reflected off the front mirror. And if you put the displacement right enough, those two will interfere destructively and not allow the light that was actually reflected to escape. because of destructive interference. So it's forced to go one more trip back and forth, and then it will interfere with the light that was supposed to pass through. And you can get this sort of interference effect that forces the light to not escape the cavity, even though you have a reflectivity of the front mirror. So this is called, as I said, impedance matching, and it enables you to get all of the light to not be transmitted, but absorbed in the atoms and in the comb. Okay, we use here another material here, thulium, yttrium, aluminium garnet. And it has a longer excited state lifetime, and we can better get rid of this background absorption in this material. And it has still a fairly large inhomogeneous line width, so we can still get a large bandwidth, but narrower than lithium niobate, but still, fairly large. Okay, and instead of putting the material inside a cavity with mirrors, we actually coat the crystal with mirror coatings that match the reflectivities we want. At least that's what we thought. And then, as I said, everything has to be in cryogenics. So we have to put it inside a cryostat here. This cryostat's an ADR, adiabatic diamagnetic refrigeration cryostat, which in this case goes down to, the one we used for this went down to in principle down to 30 millikelvin, but I think we operated this particular experiment at around 500 millikelvin. So it has to be pretty cold. That's the only disadvantage. Here's some reflectivities, and here's actually a picture of the crystal here. So you have some coatings on that gives you these different colors. Here's inside our cryostat. This sits down here on the tower here inside a magnet, so we can apply a magnetic field. And then we have light coming in from the side here. We have these little alignment tools here, electrical translation stages, so we can align the optical path into the crystal. So if you look at the first kinds of measurements we do, we just take a external cavity diode laser. Where did I go? There. Okay. We take an acousto-optic modulator to generate pulses and control the light. That's just basically a switch that we're using, sending it into the crystal here. And then to get the light back out, we unfortunately have to use a 50-50 beam splitter at this point here, because we of course have to get the light out again. So we lose half of the light just there, but that's something one can work on. And here is like the reflected signal that we see. So here is what we know is the atomic absorption line. We didn't measure it, but this is just from data that exists. And then here we see the cavity reflection. So you see reflection sort of like dips when you're resonant. We're seeing in the back reflection. That's why you see dips, not transmission peaks. And we see that when we get close to the atoms, it gets deeper because we have more absorption, more loss in the cavity, and actually gets wider because the line width of a cavity will also be wider when there's more loss in the cavity. So we can kind of see the presence of the atoms in all of these. If we go further out, they will be shallower and shallower as we don't have atoms. So here, and the free spectral range between the peaks here is 20 gigahertz. Okay. We do see that we're not able to get no reflection, so we're not able to get exactly impedance matching. Somehow we didn't pick the reflectivities quite right. Okay, so now we do a little bit more advanced setup. We allow ourselves to create a comb. We need to make this kind of like a comb structure, atomic frequency comb. So to do that, we have a couple of ways of doing that, but what we really do is that we take this laser here, we put the light through a phase modulator. A phase modulator takes light and modulates it. And whenever you take modulate an optical signal, you create sidebands. How much time? Nothing, right? Oh no, 5 minutes, right? 5 minutes? 5 minutes. We started 5 minutes late, right? Let me just get through this. I'll try and be fast. But anyway, so we generate these sidebands, and that actually allows you, because the phase modulator is driven by an electrical signal, then you can change that sideband very controlled way, and you can sweep the laser frequency basically, and then turn it on and off to selectively only address the atoms in these gaps here when you want to move them, but not touch the ones that are in the peaks. So that's how we generate the comb. And then afterwards, we switch over to this branch where we have an intensity modulator that can just create really short pulses. And then we send them into the memories, store it, and then retrieve it onto the detector. And so let me just show this. Here's an example of this comb. Here's a 500 megahertz bandwidth comb. And here is an example of such an echo. It's a little bit noisy here because just the light levels were low, but this is the mean photon number that we're using is 0.5 photons per pulse. And we see a little transmitted peak, and then we see some echoes here. And if I look at it here, this is the actual input pulse that we can show. So this is what's transmitted. But if we just look at directly the signal before it gets into the memory, we see this blue pulse here. And based on that, we can calculate an efficiency of the memory, taking into account the losses in this beam splitter. And we get about 27%, which is relatively high. We can actually measure with the green curve here, the efficiency for different detuning, so like different places inside the cavity, and see when we're in the center of the cavity, we have the frequency is aligned with the center of the cavity, we have the best efficiency. And we also do this now for a little more complicated setup where we have same laser, but now we send it into spontaneous parametric down conversion crystal. That's a crystal which is basically a entangled photon pair source. And now we do the same as what we did before. We have one detector just heralding the presence of a photon in the other arm here. We have some filters, a little bit technical, but basically this allows us to store real single photons. And in the quantum community, that's much, much better than storing photons that were generated just from a laser. Again, because of the statistics, it's important to show that it can work for sources that are at sort of more reliable single photon sources. Okay. Then we do a bunch of analysis to show that it is quantum. And what you look at there is you look at this cross correlation function. You're basically looking at this signal compared to this signal. And then you can do some analysis statistically to show that the numbers are the amount of correlation is something that couldn't be achieved if it was a classical photon signal. The statistics of the photons that were stored and detected follow something that's not a coherent state, which is the classical state, and it's above a certain bound if it's above 2 here. So we see that we get these cross correlations to be way above 2, before more than after because of loss and signal of noise, but it's above 2. And we also can do some analysis on time bin qubits. Again, here we compare the input and the output signals. We say like how close does the qubit state look after storage compared to what it should be. And from that, we can get this number, which is called the fidelity. And we get that it's 85%. For those of you yesterday who can remember from single photons, the limit for the fidelity of a classical measurement was 2/3. So if you're 85 and outside the error bars there, it means you're also having a quantum memory. Okay, so this is the full setup and the diagram shown in the paper. You see, pretty good actually. So I wanted to just mention we do a couple of other things in the lab. So we do work with more rare ions. We work with terbium, YSO. We want, this is the thing that we showed here. We have work on spectroscopy of some of these materials. And we want to also do quantum memories for microwave signals, which are the kind of signals that are used in quantum computers. So we can get a link between the optical channels and the kind of signals that are used in a quantum memory. And completely out of the blue, we're also doing stuff in quantum biology, because it turns out that some of the theorists are really interested in maybe photons playing a role inside neural channels. One of the things that would be required there is that there are photons in the brain, and that actually has been proven that biological tissue emits photons. They're called ultra-weak photon emission. And we have some really good detectors for that kind of thing. So we are pairing up with a bunch of collaborators, some biologists and some medicine people, to try and measure the properties of these photons, because that is going to tell us a little bit about what kind of process inside the tissue actually generates these photons. That's not actually known at this point. So that's a brand new research area we're working on, and we're getting some really state-of-the-art detectors from our collaborators at the Jet Propulsion Lab, some really big area detectors so we can detect a lot of light. I'll be quiet now.
Thank you very much, Dr. Oblak, for your lecture. We'll now move on to the question and answer session, for which we will only have time and space for one question.
I'll be around, right? So just ask questions.
To our Zoom audience, we remind you that you can send your questions to Dr. Oblak by sending a direct message to the person named in Plexis Q&A. For our audience in person at the Congress Center, you will be informed when you can ask your questions directly to Dr. Oblak.
Elaine, thank you very much for your talk, for your speech. I was thinking that in recent years there is available for us merely mortals access to quantum computing, for example, Google and Amazon, but I think they don't have a quantum cloud. I think there's just isolated servers, and we access them with traditional networks. So I think your work is a major breakthrough. Congratulations for that. And something that I'm kind of overwhelmed is all the factors that you mentioned for example, the signal loss, I don't know, well, so many factors. And is there something that in theory haven't worked for you? For example, you have the equation for the rate of entanglement distribution. Does something like that haven't worked in practice because of some unexpected physical issues that well, that my question would be, what's the biggest problem that you have encountered that maybe you had to take a step back and continue through another path, and also considering involving so much money? That I was just wondering that.
So you're asking, like, what is sort of the thing that's the biggest technical or fundamental problem currently for what we're trying to achieve in the terms of building quantum networks. And yeah, there's a lot of problems. I mean, I'm hopeful because things are moving fast, and things that seemed impossible like 10 years ago are possible now. You have to look at each of the components in your quantum network and try to solve the different parts and see which ones can you take off the list. And I will take it as an example, these detectors that we're using. Like 10 years ago, they didn't exist. And that was a problem because then at telecommunication wavelengths, you were using what were called indium gallium arsenide avalanche photodiodes, which were noisy and had to be triggered and whatnot. And so a lot of the things that would be possible today would not have been possible with that technology. And there was this new type of system that could solve that problem and suddenly enable a lot more of experiments. And I think similarly to that, when you look at sort of the technical and the practical side, each of the different components have to be optimized. We still don't have good sources of entangled photons that are reliable and can be run at very high rates and are purely single, entangled photon sources. That's still something that people are working on, but there's a lot of research in quantum dots and other kinds of emitters that seem to be able to solve that, probably within a 5 to 10 year time frame. Then we have the quantum memories. Those are definitely a problem in the sense that, they're still not meeting the benchmarks that we need for them to work, and there's so many things to consider. I listed all the things. In reality, you have to think of all of these at the same time. And it's not easy to find the system that does all of these things at the same time. If you want to do some basic, demonstrations to show, let's say, violet Bell's inequality over in a way that doesn't have any loopholes, you can find a system that works for that, but then it would not be still useful for quantum communication. So you just have a lot of things that have to match up. And then the final thing is that once you've solved each of these components problems individually, now they have to work together, right? So you have to have the quantum dots or the emitters of entangled photons be compatible with the quantum memories and the detectors and whatnot, right? So there is a lot of things that have to add up. And in that sense, it becomes kind of an engineering problem, right? You have to, a systems engineering, you have to find out what are the choices to make for each of them. Maybe the best option individually is not the best one for the system as a whole. And then on the more fundamental side, or on the theory side, luckily there are lots of good people who are thinking of tweaks to the protocols. For example, in quantum key distribution, it was about 2 years ago, a group of researchers came out with a new tweak of the MDI QKD protocol, which is called twin field QKD, which avoided, basically took the loss and took the square root of the loss that you would have. And in actually that sense, it violated that bound that I talked about because it's sort of a tweak to a protocol. So there keep being ideas of how to tweak it and how to improve it. So, people are working on it on all different aspects of it. And the good thing is there's a lot of people working on it. So there continuously are improvements.
Thank you, Daniel.
I guess.
We thank once again Dr. Oblak for his participation in the International Symposium of Physics. We would also like to take this opportunity to thank our sponsors without whom this event would not be possible: Ternium, Climate IA, HEB, and Isolenum. Thank you very much for your presence, and see you in a few moments for Carson Hicks' lecture, Proving the Nature of Neutrino Mass, which will start at 1:30 p.m. at the Congress Center.
Yeah, I'm just going to log off here.
Yeah, don't worry.
Stop share. There you go. You good?
Yeah. Just really quick before Dr. Oblak leaves, we wanted to thank him for his 3 days of participation within the symposium, and also offer you a little gift with some merch from the SIF, as well as your official paper.
Thank you. Thank you so much. No, it's just thank you guys for inviting me. It's been great. Thank you so much. I should do this so it looks like you're actually giving it to me.
Yeah.
Good.
Thank you. No, thank you.
Yes. Let me just close this. Yeah. Oh, okay. Sure. Where could I put this here? Thank you. This one belongs. I'll just leave it here with the clicker. This one. Bend the ground plug. Let's see, smart. Okay, so I don't know whose this was. It wasn't mine.